Some of you tried this thing on that. You did, because it should work. You also work. Right? And the key thing, of course, is that I'm just going to review this before I start today's lecture. If you have an h of s, and likewise, that means you have an h of omega by letting simply s become j omega here. And those filter properties could be low pass, high pass, band pass, or band stop. If you have that, and you want to turn it into a discrete time filter, something that can be used in the discrete domain, then you can take this and simply have h, and this would be discrete time, where z is equal to 2 over t, and that would be the sampling interval, times z minus 1 over z plus 1. This is, I'm sorry, s. And here t is simply the sampling interval. So that'll do it. And this is h, then it'd be h of z once you did this transform. And then from there, if you want to see what it looks like in the actual omega domain, then you simply take this and let z become simply e to the j omega, and then you would be in the discrete time Fourier transform domain, or the omega domain, but now it's sampled. Are you with me, class? This is that's what my goal was on Friday, and I gave you a simple example. The filter, did anybody plot the properties of the filter I gave you? As a low-pass filter, it's called a Butterworth filter in S, and then you can let S be j omega, and then if you do the transform, you get a low-pass filter, and if you, in that plot, you actually saw it. Did you all see this, class? How many actually did this? Just show me. Nobody ran this thing in MATLAB, I think. Did you run it in MATLAB? No.
I kind of, I had a hard time getting the conversion from the continuous to the discrete.
Well, I actually put the solution up there. Did you see that?
I didn't see the solution.
Isn't that up there? Didn't I give you a MATLAB code to run in there? Or no? I thought it was on OneNote. If it isn't, I'll go through it. I gave you that. This is really the transform. If you take what S was and replace it by this, then you should get a property that you can plot where you get an h of z, and then from h of z, let z equal e to the j omega, and it should plot it very well. You didn't see that, though? Then I'll show it to you when I'm done with this part of the lecture. All right? I have things to show you. But the bottom line is, you can take information you know about continuous time filters and turn them into discrete time filters. That's the goal of Friday's lecture, and that's important. This transform right here is an approximation, and it boils down to the log z. Natural log of z is really going to be 2 over z minus 1 over z plus 1. And that's how that works. But now today, I'm going to talk about things, and I have this, I'll do this example down here. I have my computer and stuff. I'll do it at the end of class. Today what I'm going to be talking about was, didn't I put down h of d as what it was, is 0.032 times z squared plus 2z plus 1? Isn't that on OneNote? Over z squared minus 1.41, or 1.45147 z plus 0.5724. Didn't I put that down there? Well, I'll check, and I'll put it up there. That's the result after everything is crushed together in the z domain. All right, now, today, to get to that, we're going to be talking about something called, first we talked about really, on Friday a bit, IIR filters, and this is infinite impulse response filters. Let me make a statement here. Don't let this bother you. This, believe it or not, is an impulse, it's an infinite impulse response filter. You just didn't know it. Because it was, the whole goal of Friday was just show you how to convert it. Here, when I talk about IIR filters, what it means is this. H of n here will go on forever. More or less, this will have values for all n. So even as n goes to infinity, an infinite impulse response filter will have some value. It may be tending towards 0, but it'll have a value. That's an infinite impulse response filters. Are you with me on this, class? Now, there's also one called a finite. I'll put it right here and I'll get to it. It's called a finite impulse response filter. That's called an FIR filter. It just means finite versus infinite. That's the only difference. And here, the big difference is h of n will have values that are possibly non-zero values here. I'll just put values. For n greater than or equal to 0, less than or equal to some n minus 1. The length of this will be n, and it will be 0 else. So it means that the actual impulse response only has a finite duration. That should make sense. Why is this important? Because this is something that's reasonable to create. If it's got a finite, you might say, impulse response, it's something we can catalog in real life and use. Are you with me, class? That's the big difference. You'll see more in a second. So now, come over here.
What is that written below 0 less than beginning? What's the last, it's like it equals 0?
Else. This is else.
Okay, thank you.
I'm just trying to say it has a finite duration. The impulse occurs at 0, n equals 0. H of n is a response to the system to that, and it's not going to go on forever. That's what I'm saying. This one, for an infinite impulse response systems, it possibly can. All right? In other words, if you have, for instance, 1/2 to the n, u of n, even as n goes to infinity, it's tending towards 0, but it has, say, at 1,000, it still has something there. With me on this, class? It goes on forever. Where if you just chop it off and says it stops at a certain point, it says it's 0 after that, then that's something we can work with computers. Now, so back to the IRR business, the infinite impulse response filters. I wrote down a bunch of stuff. What I want to do is try to explain several things about this. If you think about this, all these things are types of what they call moving average filters, whether you know it or not. It's because they store information and they're doing some kind of averaging with it. They're actually called auto-regressive moving average filters. And you'll see this, auto-regressive moving average. That's filters. You're going to see that. Has anybody ever seen that logo before, or seen that? Auto-regressive, you know, regressive filters or something, where they take values for information from past times and they use those values to calculate future time values. That's a regressive filter. It's using a regressive state of values to do it. Now, in general, when you're dealing with any kind of a system, where you're talking about discrete time, you can catalog, or you can, any of these systems we can write in terms of differential equations or difference equations. That's in time when we're talking about input to output, x and y. Or we can talk about or we can talk about transfer functions, h of, say, s or h of omega, or h of n, or we can talk about convolution, and I'm going to do all three of them. How y of n is the convolution of h of n times x of n, all right? All of those things detail how a system responds. Are you with me on this, class? So this is one thing to take in mind. If we did it with a difference equation, we're talking about using filtering in discrete time, then your difference equation would look something like this. In general, this is a general form. You would have some y of n plus, and I'm going to use a1, y of n minus 1 plus a2, y of n minus 2 plus plus a to the n y of n minus, small n minus capital N, where n is the length. And let me get rid of this, and I'm going to show you how this whole thing is going to work. Now, if we have this, that's just going on forever. That's equal to, I'm using the way the book does it, x of n plus b1 times x of n minus 1 plus plus and then it will be b to the m x of n minus capital M. This is just a difference equation on both sides. Now the reason you call it a moving average or an autoregressive moving average filter, if you just look at this for a second, this entire thing is taking the current value of x of n or past values and weighing it by some constant, right? If I wanted the value of y of n, if I take this and then I subtract this from it, on the other side, all this, then I can predict y of n. But it's simply storing information and weighting that information by some constants to get the future value. Are you with me, class? Now, if you have that, and you look at the z transform of this, I'm going to do a z first. Then you're going to get y of z here, times, and we're assuming there's no state information at z equal or n equals 0, so there's no initial conditions, think of it that way, to worry about. Then I get the transform of y of n becomes simply y of z, or 1 times y of z. The next value is going to be what? Plus a1 times, class? Z transform. Z to what?
Minus 1.
Minus 1, right. Make sure you know that. Minus 1 plus a2 times, right, and it keeps going on and on. Dot, 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 plus a to the n, z to the minus n. All that equals, and then here I'll take out the x of z, and then I get b0, right, plus b1 times z to the minus 1 plus dot, 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 and then it would be bm z to the minus m. Now you can plainly see here, this is very easy to do. This is the reason I chose to do it this way. It's very obvious what I'm doing. There's nothing hidden, no kind of crazy convolution. Now when I take a look at the transfer function, the h of z for this, that's going to be equal to simply y of z over x of z. Are you with me on this, the whole thing? And then that's going to be simply equal to b0 plus b1 z to the minus 1 plus dot, 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 plus b to the m z to the minus m over 1 plus a1 z to the minus 1 plus a2 z to the minus 2 plus dot, 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 all the way out to a to the n z to the minus n. And this should make perfect sense to everybody. Here we're just putting it in terms of a ratio of two polynomials, right? Now, this particular thing here, the h of z, has poles at certain values. You might not be able to see where the poles are just the way I did it. Obviously, I can't either. But obviously, you know, poles are values that turn this function into, it's going to tend to infinity, where the pole is, right? So you're going to have a series of poles. The poles occur at really z equal to, matter of fact, just call them at p sub I. The poles, there's going to be a bunch of poles, and I'm just going to label them as p sub I. For instance, well, I'll give you for instance in a second. So if those are the poles, that means the impulse response, and I'm going to justify what I'm saying, if I take a look at this, then h of n, the impulse response of this, is simply going to be equal to a sum of I equal 1, really to the number of poles, you might say n, because there's possibly n poles, of some c of I, and that is just a constant that we don't know, times, and then it's going to be the pole value itself to the nth power times u of n. Or I'm sorry, I power, not n power. This is I. This is p of I. This is in the book times, this is to the I. Now I'm going to give, because a lot of this doesn't make perfect, it'll be more clear if I give you an example. Now, what I'm really saying is these are the poles taken to the I power. C is some value we would get by the cover-up method when we do the expansion, partial fraction expansion. Remember that, how we always calculate the constants for each of those poles? And u of n just says it's going to be valid for n greater than or equal to 0, and 0 before that. Now, when I look at this h of n here, as an example, suppose I gave you h of z was equal to 2z over z minus 1. One look at that, where's the pole? P1 only. Class, z equals 1. All right, what if I made it 1/2? Where's the pole? 1/2, right? Therefore, h of n here would be equal to simply 2 times 1/2 the pole value times u of n, right? And this would be to the n power. Are you with me on that? Just so you understand what I'm talking about with poles. That's the easiest possible thing I can think of. That's a very simple pole 0. Where's the 0 in this one, by the way? I didn't mention that. Z equal 0, right? At 0, it's 0, correct, class? 0 over minus 1/2 is still 0. Agreed? Just so you know, in the discussion in the book, he may mention that. All right. So, getting back to this is sort of IR filters. And by the way, on Friday, when I went ahead and I took a very simple difference, I took a h of z, and I took h of z, then I turned it into really y of z times something and x of z times something. Do you remember that? And then we turned that thing into a difference equation. Do you all remember that, class? We turned it into a difference equation. That's effectively what this is. It's an infinite impulse response filter. Recall when we do that and we look at this, the impulse response, technically this thing exists for all values of n greater than 0. Even though it's asymptotically going to 0, it still exists for those values. Follow me? Understand? Now, and that makes convolution. If we can't store all this information and then use it to convolve it, that's because remember, this kind of a difference equation right here, right? I mean, this first difference equation, to get y of n from x of n, we could do it that way. You with me in this, class? I could take all these values, this is a regressive type thing, it's an average of all these values weighted by the b constants, and and subtract it from all those values that I have circled there on this side to get y of n. Or I could also get y of n by doing what? I could say y of n would be equal to h of n, whatever this was, convolved with x of n. Understand? Now this accomplishes the same thing that difference equation does. Do you understand that, class? But to do this, what? I would need the values of h of n stored from n equals 0 to infinity, theoretically, or a very large value. Follow me on that? So the difference equation, frankly, is probably an easier way to do it. This, however, is something that we're looking at because convolution, believe it or not, in time domain convolution is less operations than that in general, if this is finite, not if it's infinite. So now that I've said that, now I'm going to talk about not an infinite impulse response, but something realistic, a finite impulse response filter. And you'll see why I'm doing it. Some of this is going to be a little odd, but I'll try to make it as clear as possible. All right. I normally don't like carrying notes. I'm doing this today because I want to make absolutely sure I don't use symbolism that isn't consistent with the book. So this is going to be FIR filter. All right, that's a finite impulse response filter. So with that, again, remember that y of n is equal to x of n convolved with h of n, and the order makes no difference. It can be h of n convolved with x of n. But that's using convolution to define the output. We all know that. You've seen convolution since really the first week and a half of class. So in general, for a finite impulse response filter, it means that h of n is going to have some values b of n for n greater than or equal to 0, less than or equal to some value m. Now, first time you see this, it doesn't mean a lot, but let me give you an example. Is that mine? Let me give you an example of this. Suppose I said h of n, and then it's 0 else. It means for all other values it's 0. Now, I'll give you an example, because you look at this, it doesn't mean much, all right? It just doesn't. Let me give you an example. Suppose I said that h of n, and I'm going to do it in terms of a simple vector, was equal to 0, 1/2, 1, 1/2, and 0. It's already got 2 zeros at the end, but it's 0 anywhere else. So what is that? That looks like basically something that's trying to be a triangle right there, if you look at it. Starts at 0, goes up to 1, back to 0, and it's the half's one thing. Well, if that's h of n right here, I can figure out my h of z very easily. Do you all agree with that? I mean, I don't know if I need to do it, but I'll just do it right here quickly. You don't need to write this down. What is it going to be if I take a look at this and do my h of z? That's equal to the summation, right, of h of I, really h of n, might as well just put h of n, times z to the minus n, from n equals really, say 0 to 4. But really, it's going to be 0 times z to the 0 plus 1/2 times z to the minus 1 plus 1 times z to the minus 2 plus 1/2 times z to the minus 3 plus 0. Or really, this in fact is the z transform of that. Are you with me, class? Let me finish my thought on this one. So really, if that's the z transform, that is my h of z. I know h of z is equal to y of z over x of z, right? And now I can come up here and I can say that if I take this, if I wanted to do it, I could say that well, actually, at this point, I could develop a difference equation, but I'm not buying myself anything by doing it. This is I've got the h of n and I've got h of z, so I can just use convolution. I don't need a difference equation to describe that. But if I did want a difference equation, what could I do? Anybody? Pardon me? Well, you know, a difference equation is really what? You want x of z on one thing times some of that, and y of z on the other. Well, if I take a look at, if I multiply top and bottom, call it 1 here, by z cubed, all right? Then watch what you get. I'm going to say I would have y of z here over x of z equal to, and then I'm going to have, that's going to be 1/2 z to the minus 1 plus z to the minus 2 plus 1/2 z to the minus 3 all over 1. Are you with me? I'm just putting a 1 down there. Understand, class? Now if I multiply top and bottom by z cubed, then I'm going to get z squared here. I'm going to get z here, right? The 1 power. And then I'm just going to get 1/2, and I'm going to get z cubed here. Do you all agree with me? And then that means if I multiply both sides by z cubed, I would get z cubed here. And then if I multiply both sides by x of z, now I get x of z there. Are you with me? Right? I'm just showing you, now at this point, maybe I didn't have to do it that way, but, and then if I would divide everything by z cubed, this is sort of a backwards thing. I wanted to make sure you saw this, then I would get 1. This would be z to the minus 1, z to the minus 2. And finally, this would be z to the minus 3. And then I could say that what? Y of n was equal to x of what? It would be 1/2 times x to the what? N minus 1 plus simply x to the n minus 2 plus 1/2 x to the n minus 3. Are you with me? That would be, I wanted to show you, that would be the difference equation. It's much easier to do it I'm just using that convolution operator. The reason it starts at n minus 1 is because there's a 0 right there. I assume it started there. All right, now, so that's my spiel about what this means. They're just coefficients right here. They're values, and really that's all they are, single values that we're going to use for convolution. I'm going to get rid of this. I want to use this part of the board for what I'm about to do. Now, in general, I could say that y then here was equal to, and it won't matter the order, x of n convolved with h of n here. If I take convolution, discrete time convolution is I equals 0, really to n, you can go to infinity, but it makes no sense to, of really x of I times h of n minus I, or it's also equal to, since order means no difference, it could be x of n minus I times h of I. The order makes no difference. That's the definition of convolution. Do you agree with me, everyone? All right, now, if you take a look at this, right here, and you look at this one right here, I can say, matter of fact, why don't I change the order of these things? Let me put it down here. I can say that this is going to be the summation from I equals 0 to n of h of I times x of n minus I. And you'll see what I'm up to. I just took these two and put this one first, the h of I. So now this becomes, well, at I equals 0, right here, that would be b0, right, times x of n. Now notice when I is 0, x of n times h0, which would be b0, would be the first entry. Are you with me, class? You follow me on this? If that's b sub n equals 0 is the first entry here. Then it would be what? Plus b1 times x of n minus 1 plus b2 x of n minus 2 plus plus b to the m x of n minus m. But again, this is finite in terms of its extent. So y of n can be calculated via convolution in the discrete time domain by using a finite number of coefficients that multiply the incoming sum. Now, y'all see that this is still a moving average filter because it's really averaging all the values, right, from n to some n minus m by weights. And then that average is frankly what you're calculating. It's a moving average filter. Are you with me? I'll just give you a tip on these. Anytime you see the actual sign change on this is plus, this minus, this plus, this minus, that's a high pass filter, or possibly band pass. Anytime these signs are all positive or all negative, it's a low pass filter. Remember that. All right? I'm just telling you that much. They don't tell you that in the book, but I know this. So that's one way, just by looking at the coefficients, you can tell what kind of filtering is going on. And I'm going to give you examples of this in a second. Now, I got to tell you one other thing too, and this is something that's real important. You see, this one is going to have a response. Remember, what does h of n really indicate in your own words? When I talk about h of t or h of n, what is it in own words? Anyone?
The system to an impulse input.
And where does the impulse turn on it?
T equals 0.
Or n equals 0. With me?
Yeah, any.
Now, that means this is a causal system, because look, all the outputs occur for 0, n equals 0, or n greater than 0, right? A non-causal response would be something where you had h of n values that were non-zero for n less than 0, all right? But if you did have a non-causal impulse response, and you'll see why it's important, you can make it a causal response. Let's just say we had h of n here. That's going to have values that are non-zero, that has some values, b of n, for n less than, or from some minus m over 2, or minus, pardon me, from minus L over, just minus, minus L over, I think I can just go from minus L, yeah, that'd be fine. Minus L less than L. So it's going to have some values and then 0 else. This is symmetric for n equals 0. All right? In other words, well, maybe not symmetric, but it has values from minus L to plus L. It's finite duration in 0 else, but it's not causal. Because why? Because when n equals 0 is when the impulse hits the system, right? But for n equals 0, less than 0, we've already got responses, which is an impossibility. It's non-causal. Are you with me on this, class? That's the reason this is not causal. But we can make it causal. We can say that n, call it causal of n, could be equal to simply h of n, and then we delay it by simply L. Now that's shifting everything to the right. So now this filter down there would start at n equals 0. Are you with me? The impulse response. With me, guys? You're going to see it's applied in 1 second. Some of this stuff you really have to focus on, because you're going to see this over and over and again in your classes. Your guys, right out of here, the next class you get are what? Random signals and systems, which takes probability and wraps it into everything you're learning. And you have to kind of, and you're going to have Dr. Reeves, who's a very good teacher, but also he expects a lot of his students. You have to understand that's non-causal, this is causal. That's something that we can build and can see. All right? It's something that's real. All right. Now, yeah, I got all that down there. I'll take you to the next. Next step is building some of these. And that's what my real goal of this is. That I'll say one other thing. What's the relationship between these two if we did in the Z transform? All right. If this h of n went to some h of z, right? What happens when we get a shift like that in the frequency domain? It's going to be what? That's right, times simply h of z. It's only a, and when you put z equals to e to the j omega, it's simply a phase shift. In other words, the magnitude doesn't change. That's my point here. Magnitude doesn't change, just phase. Anytime you get time delay operators, you're always getting phase shifting in the frequency domain. It's real important to note that. All right. Now, several types of filters. These you know, I have to put them down because when we start doing some of these things, I need to make sure you clearly understand what I mean by it. Ideally, if you had a low-pass filter, and here we're going to assume Z now becomes e to the j omega. For a low-pass filter, the desired h of omega here would be equal to 1, this is at least one possibility, for some values of omega greater than or equal to 0, less than or equal to some omega low, and then equal to 0 for magnitude of omega greater than omega low and less than pi. Now the reason I'm showing you this specifically is this. With filter design, you have to understand this. We know everything repeats itself every 2 pi if you're talking about h of omega, right? We know that. Now when we talk about a low-pass filter, we're really talking about this, an ideal low-pass. That goes from some omega low here, minus omega low here, has a value of 1. We know this isn't going to work. We know it's going to give a non-causal response, but I'm going to show you how to adapt this into a causal response, something that you can actually use. So that's h of omega right there. That's for low pass. This is, the D here simply indicates desired. It's what we want. And that's low pass. If we talk about band pass, and this will encompass high pass, a band pass filter has h desired of omega equal to 0 for the magnitude of omega here greater than 0, less than some omega low, and it's going to have a value, this is ideal by the way, from magnitude of omega greater than omega or equal to omega low, less than or equal to omega high, and then it's going to be equal to 0 for our values of omega greater than omega high and less than or equal to pi. Now, what that would look like, this is a low pass, by the way. H desired, this is a low pass filter. What this one will look like is this. It's just like this, basically a notch. The height of this is 1. And that's what the filter looks like. I'm shifting what? I'm shifting this. Looks like I'm multiplying it by a cosine, but now it just shifts. Now this is the band of frequencies that will pass. Are you with me? By the way, what would a band stop be?
It would be 1 minus.
1 minus that, isn't that
Yeah.
right? That would be a band stop. It means it stops those bands of frequencies instead of passing them. And we can, in the limit, turn this into a high-pass filter. If omega high became pi, then it would be a high-pass filter. But again, I'm showing you ideal concepts. You've all seen these, right, class? You've seen these concepts at least. All right. Neither one of these is useful for actual real-time filtering. But if you have a data record, you can use this because then you have all possible values. You know the future and the past values, so you can use them. Now, come back over here. Now we're going to actually build some filters. I mean, we're going to create filters that are realizable. And I could talk about a differentiator too. I'll just put this down there. There's also a filter that's common. It's a differentiator. A differentiator. And that just has the desired h of d of omega equal to j omega. Now, a differentiator is really used for speedometers. All it's doing is finding the rate, it's taking a look at how fast, if you think about this, if this is the response, right? It's looking at how fast something is spinning, you could say. And I'll spend more time on this, but that's the actual responsive differentiator. Like if you have a filter where say h of omega was omega, right? What is that really telling you? Well, the faster something moving, the greater the output is, and it's linear proportional. Isn't that what a speedometer really does? Basically, it's just what? It's a linearly proportional to the velocity. And that's all this is, only they use the J in front of there because there's going to be some tricks they'll play on this later. And that's a differentiator. I don't want to mention the Hilbert, it won't make much sense to you. So now I'm going to go ahead and design an actual discrete time, or a finite impulse response filter, but I'm going to build something that is actually useful for us and can work from the ideal. All right. So now if we have, here's the example. If I have h desired of omega equal to 1, and I want this from 0 greater than or equal to omega less than or equal to pi, magnitude that, and 0, or pi over 2, pardon, pi over 2. I got pi over, yeah, pi over 2, and 0 for omega greater than pi over 2, less than or equal to pi. This is a low-pass filter. From 0 to pi over 2, it passes everything. From pi over 2 to pi, it doesn't. So if that's the case, then I can show you, let me just do this for you. I gotta review, this is a good time for me to review one concept. I'm not gonna need these notes now. Y'all agree, first of all, that's a low-pass filter. Everybody down with that? All right, now if it's a low-pass filter, and I know I'm in omega domain, something you need to know. Remember that x of omega, this is the general property, the DTFT. We could do it with a z, but it's better with the DTFT here, I think. Is really equal to a summation of x of n, and in this one starts from minus infinity to infinity, if it's a DTFT. Times what? E to the minus j n omega. That's the summation, the discrete time Fourier transform. Y'all agree with that? Also, if we had this information, then x of n would be equal to 1 over 2 pi, the integral from minus pi to pi of x of omega, that's the DTFT, times e to the minus j, or I mean plus j, and omega d omega. The reason I wrote these two down here, it's been a while since you've seen them. Remember, this one starts at minus infinity. That's the key. It doesn't start at n equals 0, the DTFT. Are you with me? Now, that's the x of n you get. I mentioned this several times before that we can use this. I said this was always what? There's a term I used for the first one. Anybody? It goes to the continuous time Fourier transform too. Anytime you get a continuous time Fourier transform of something, or a discrete time, you're analyzing, right? This one had the term of, anybody? Synthesizing. We're creating if we're on this one. Now, look here. My x of omega is actually my h desired. Follow me, guys? Please watch this. That's what I desire. I'm synthesizing something. So when I go ahead and do this, now I find out my x of n is what? Is equal to 1 over 2 pi, but not from minus pi to plus pi. A value of 1 only exists from minus pi over 2 to pi over 2, right? So now I put minus pi over 2 to pi over 2. It's got a value of 1, which makes it nice, times e to the j n omega d omega. Are you with me so far? I'm going through every step of this. The book doesn't, but I want to make sure you see this. Okay? We're synthesizing now. And this is no longer x of n, it's what? H of n, right? It's specifically the impulse response. So what is it? What do we get from this one? We get 1 over 2 pi. The integral of e to the j n omega d omega is what? 1 over j, right, times n, isn't it, class? Right? And then we evaluate e to the j n omega at bottom and top, or top and bottom, so I get e to the j times n pi over 2 minus e to the minus j n pi over 2. Anybody want to take a guess at what I do next? Surely you guys know this one by heart. What?
Maybe sine function.
I'm going to do what? I'm going to take this and say that's really 2j times the sine of the argument n pi over 2, correct? And then I see a j down here, but I'm going to write the whole thing out for you first. So I have 1 over, and this would be j times 2 times pi times n, and then there would be 2j times the sine here of n pi over 2. Are you with me? I'm just going ahead and taking that, turn into a sine. What happens next, guys? Am I looking? Say again? 2j's cancel. And now I have 1 over pi n times the sine of n pi over 2. Right? And this is for all values of n. Now that is not causal, is it, class? Take one look at this. If this is true for all values of n, then when n is negative, it still has non-zero values, right? Remember, this whole deal with this is a response of a system to an impulse, a delta of n that occurs at 0. That means before it happened, we would have a response. Follow me? So we're going to have to do two things with this one. I want you to listen to it. I didn't mention this last part. The first thing we're going to do is truncate the length of this. And after we truncate it, then we're going to shift it all to the positive time domain for n equals 0 and upward, all right? Now listen what I'm doing here. I'm going to say now I'm going to truncate it. I'm going to say this exists only for n greater than or equal to minus 5 and less than or equal to 5. So, and it's 0 else. I guess I didn't say this, but the way we actually do FIR filters is we start with an infinite impulse response system, and then we take the impulse response and we truncate it down to something finite, and then we shift it, and then we modify it even further to make it more usable. But you'll see these, I'm going to go through all these steps with you. Are you with me on this? By the way, what's the total number of non-zero points here, or possibly non-zero? It's not what, 10, it's 10 plus 1, right? Because the zeros are included. That means you put down L equals 11, and that's important. L equals 11 there. Now, coming back over here. Now what I do is say, I took you through that development. All right, so here's the two things I'm going to do. I'm going to shift everything by 5, number 1, and I'm also going to multiply by a Hamming window. The reason I'm using a Hamming window for this particular thing, it'll make the response, it'll have less ripples, if that makes sense to you, all right, in the response. It's going to have less oscillations, oscillatory properties. So first thing I have to do is to take a look at what a Hamming window is. For this window, remember, in general, this is a Hamming window. It's equal to 0.46, or I'm sorry, 0.54. I got it backwards. 0.54 minus 0.46, and it's times the cosine of 2 pi n divided by L minus 1, which means for ours it's 0.54 minus 0.46 times cosine of 2 pi n divided by 10. The reason it's 10 is L is 11. Please just listen to me. Now that's the Hamming window. A Hamming window supposedly starts at n equals 0. Do you remember that? The whole thing with windowing is we start them at n equals 0. But our actual function here starts at minus 5. So here's what I'm up to, guys. Just listen. I know I'm almost done, out of time. First, I'm going to shift the Hamming window to start at n equals minus 5. Got me? Then I multiply that shifted window by this. And then I take the multiplication of this times that and shift it up to n equals, so it starts at n equals 0, all right? That's the goal. So now, when I shift that, I am out of time. I'll tell you what, I'll do this in the notes on this one. I want to get through this and show you guys how to really build filters, digital filters, and not play around just with a lot of theory and hand waving. I want to actually do this. I'm going to do it next time. I'll put some notes up there, and I'll make sure that the solution is there. Please stay with me on this one. I'll tell you what's going to be included on the final from this specifically. Please come to the next slide. Are you with me so far with what I'm up to, at least? Kind of, sort of. The whole idea is this. I want to build a filter. I want to build the easiest to build digital filter I can, which means the minimum amount of memory storage elements and the maximum amount of, I guess, filtering. And I'll show it to you. By the way, if you want to see what this is,